Hello, welcome to an extra review video in the topics of the extreme value theorem, the L'Hopital rules, and antiderivatives. The goal for this video is to present one problem in each topic involving parameters inside of the functions being presented. So these are more conceptual types of problems that you should really only watch this once you're sure that you understand the more basic types, the standard types of problems. But these ones here will probably, hopefully help you understand the process of how these problems work. So this first one about the extreme value theorem, we're going to have this parameter p inside of the function. Consider the function below where p is some number between 0 and 12. This is a function of x, but there is a p inside of it as well. And x is in the domain 0 to 2. So the question is saying if the global max of the function f in the domain provided is 2, then what is the value of p? So the global max value is equal to 2. This is kind of different from the normal problem where you're given a specific function and they just ask what is the global max. This time they're giving you the max and asking for the p. So what we have to do in here, follow the procedure from this function, the procedure that you would normally do to find this global max. And then that's going to be an expression depending on p. If you set that expression to equal to 2, which is the value that you know is the max, then you're going to be able to find p. That's the idea. Okay, so we have the function f. You know that the function is continuous. It is given in a closed interval, so this global max must exist. That's the extreme value theorem. And the only locations where it could possibly happen are the end points or extreme points of the interval, 0 and 2, as well as critical points. And for such a simple function like this, the easiest thing that you can try to do is check the value of the function in each one of those points. Whatever is the largest one will be the global max. So let's go ahead and find f of 0. That's very easy. If x is equal to 0, you see that there's an x in each term. So that gives you f of 0 equals 0. And then what is f of 2? That one's going to depend on p. Plug in 2 for x. The first term here will be 4 times 8. Second term will be 4 times 4 times p. So 16p. And the last one, 2p squared. So whatever this number is, we don't know, like just looking at it, it's difficult to understand which one of these is actually largest, 0 or the other guy. So we have to keep working now to find all the candidates for max value. What is f prime in order to find critical points? F prime of x is 12x squared minus 8p times x plus p squared. Looking at f and taking the derivative. If you're looking for critical points, you're going to set this equal to 0 and solve. This is not easy to factor, so you probably want to use the quadratic formula. X is equal to, so p is part of the numbers for this equation of the coefficients. X is the variable. So for example, the thing that we usually call b is this minus 8b here. And you want to do minus b plus or minus square root of b squared minus 4 times a times c. C is p squared. Divided, the whole thing should be divided by 2 times a, 24. Now calculate this. This first square here will give you 64p squared, and then you're subtracting 48p squared. That leaves you with 16p squared, and the square root of that is 4p. So this simplifies a lot. What are those two numbers then? If you select the plus sign, you're going to have 12p over 24, which is p over 2, or if you have the minus sign, 4p over 24, p over 6. Those are the two critical points of your function. And there are no points where the derivative does not exist. So you go back to the original function f and evaluate it at these 2 points. f of p over 2 and f of p over 6. So for example, plug in x equals p over 2 into f right here. 4x cubed minus 4px squared and then plus p squared times x. I think that's right. Yes. So what does this give you? Every term here is going to have a p cubed. Look at this, p squared times p squared times p. Every term has a p cubed. And what do you have in terms of the numbers? You're going to have 4 over 8 because of this cube here, minus 4 over 4 plus 1/2. So this is 1/2 minus 1 plus 1/2. That's going to be 0. So you do a similar thing for the other one, f of p over 6. This one will give you an actual number. Once again, the powers of p will all combine and give you just a p cubed, but the numbers turn out to give you 2 over 27. Try this for yourself. So I'm going to circle these as well as the other two values that we found. These are all candidates for being the max. Now, okay. The problem told us actually that the max is equal to 2. One of these guys has to be 2. It's not, certainly not the first one, which is 0. It could be the second one here, or it could be this last one. So based on what the problem told us, one of these guys, what is this one? 2p squared, I think. Yes, minus 16p plus 2p squared. Or, so this one, or 2 over 27p cubed is equal to 2, whichever is largest. So by setting each one of these guys equal to 2, you should be able to solve for p. And then verify that for that value of p, the one that you just plugged in is indeed the max. That's what I'm going to do now. For which p's does either of these expressions actually equal to? Let's check the first one. Is this equal to 2? Well, divide everything by 2 here and move things around. You have p squared minus 8p plus 30, so plus 15 after dividing by 2 equals 0. This one, you can use quadratic formula, or in this case, it actually factors very easily. P minus 3, p minus 5. So p must be equal to 3 or 5. Both of these are possible. They're valid values for p. Remember, the question gave us that p is between 0 and 12. So these could be potential values of p. However, if you think about this, when p is equal to 3 or 5, what is happening to the other expression? If that other expression gives you something larger, then that cannot be the value of p that you're looking for. Because remember, not only you want one of these guys to be 2, you also want it to be the largest. You're looking for the max. So when p is equal to 3, the other expression, this one, what does that give you? 2 over 27p cubed. That's an easy computation. 3 cubed is 27. The 27s go away. So the other one is also equal to 2. That means you're in good shape. If p is 3, both expressions, maybe I'm going to give them names. I'm going to call them like 1 and 2. Both 1 and 2 are equal to 3. Sorry, are equal to 2. And are the max value. However, for this other value of p here, p equals 5, when p equals 5, this other expression, 2 over 27p cubed, what is that? 5 cubed is 125. So 250 over 27, whatever this number is, that's going to be larger than 2. So if p is 5, even though the first expression, 1, is equal to 2, we have that the max is the second expression, actually, which is equal to 250 over 27, much larger than 2. So that's not good for you. This case, b equals 5, the max is not going to be 2. So all of this was the analysis of what happens when the first expression is 2. Technically, we also need to do it for the second now, but that's very easy. What happens if this one is equal to 2? For what values of p can that happen? It's actually just going to be 1, and we already found that in here. So yeah, solve this equation. P cubed equals 27, p equals 3. So we already know this is okay. So that's your answer here. The only possibility answer, p equals 3. That's the one for which the max is equal to 2. And if you think about it, we found that this max actually occurs in 2 different locations. Both of these expressions, this one, which is f of p over 6, as well as this one, which is f of 2, both of them are equal to the max of 2. Your function looks like this. It is between 0 and 2. F of 2 is 2 in this case, but also f of p over 6. P over 6 is 1/2. So here is 1/2. The value of the function there is also 2. If you try to graph this function, you're going to see that it actually looks more or less like this. So just so you understand what's happening. But the answer stopped here once you found the b. All right, so this was, it's a little longer because it's not just doing the procedure that we all usually do, but it has a p inside of it that we have to understand. We really need to understand what each step means, but I hope this is okay. I'm going to move on to the next problem. This is now L'Hopital with parameters. This one's not going to be that long. And also interesting in this problem, I'm not going to give you a specific function. I'm just saying f is some differentiable function. And we know some specific values for it at the number -3. We know the value of f and the value of the derivative. Now consider the limit below where a and b are numbers to be determined. This a is here and the b is here. And the function f also appears. But important, you're told that L'Hopital can be applied. So find a and b and find the limit. So this is important. L'Hopital can be applied. What does that mean? It means that the limit must be of the form 0 over 0 or infinity over infinity, but you know that's not going to happen. For example, looking at the denominator, a is going to be some number, and then x plus 1 is also going to some number. It's not going to infinity, right? So it has to be 0 over 0. But that immediately gives you a way to find a and b. If the limit, here's the limit. It is as x is going to a. If you were to try to compute this directly by plugging in x equals a, you would find f of 3a plus b times a squared over a plus 1. You know that this is a limit of the form 0 over 0, according to the problem. So set these numerator and denominator equal to 0. For example, denominator will give you a equals -1. And then numerator, I'm already going to plug in a equals -1 here. So f of -3 plus -1 squared is 1. So you just have plus b also equals 0. And well, even though we don't know f, we know f of -3. It was given in the problem. It's 7. So 7 plus b is 0. B is -7. So we already have a and b. With this, find the limit. So now let's find this limit. Okay, so we have x is going to -1. Now here's the thing. The function, I'm not going to replace f of 3x with the value 7. I'm not going to do that. not 7, because x is the variable in the limit. Before plugging in, I'm trying to compute the limit. I'm not going to plug in x equals -1 yet. So you see what I mean here. 7 -7 for b, x squared, and the denominator was x plus 1. This is the limit that we have. We already know that if we try to plug in x equals -1, then this first term gives you a 7, but that's a problem. You cannot plug in because it gives you 0 over 0. So you have to use L'Hopital, but you know that you can. The function is differentiable. So how does that work? How do you find the derivative of this numerator? It's symbolic in the first term. We don't know what the function f is, but we can write down the derivative. This is something that requires a chain rule. You have an outer function f, whose derivative is f prime, evaluated at the inner function 3x, and you need to multiply this by the derivative of 3x, which is 3. So that is the derivative of f of 3x. The derivative of 7x squared is 14x. And in the denominator, that's an easy derivative. Just add a derivative of x is 1. This limit, is this something that we know by plugging in? Can we plug in x equals -1? That would give you f prime of -3. Here, 3x becomes -3 times 3. And then 14 times -1 with another minus in front, that's plus 14. Does this give us an actual number? Yes, it does. We know f prime of -3 in the problem. It was 2. If you go back up, you'll see that they gave us this value, and so this is a 20. Because we find a number here, the answer is this is the equal to the original limit. So you have the answer. So you see that sometimes a question may ask you to find the parameters first. And we did it by knowing that L'Hopital can be applied. They told us that. Once you have the parameters, then you can apply L'Hopital symbolically because of the function f, but it gives you a final answer. And last one. Now this is about antiderivatives, more specifically initial value problems. Consider the IVP below, in which this number p is a parameter. So this is for a function g whose derivative is this. And g of p is 0, but we don't know what this p is going to be yet. Now you're told that a solution exists in this form where a and b are also parameters. Compute a, b, and p. So we're not being asked to solve the IVP. We want to find the parameters a, b, p. To do that, we actually need to understand what it means to be a solution. But I think it should be very clear, right? When you write an IVP, a problem like this, what you mean is you're looking for a function g with these two properties. G of the number p is 0, and g prime is this derivative here, this function. Now the function g was given to you. So try to see how to make both of those properties be true for it. Take the derivative of this function. I'm looking here. By quotient rule, I'm going to write low d height minus height d low over low square, where a and b were considered to be just numbers. We don't take derivatives of them. So we have to simplify this. You see that x minus x will go away. You just have b minus a over x plus b squared. This is the derivative of the function given. But according to the IVP, it must be equal to the function 1 over x plus 2 squared. So what kind of equality is this? When you look at this, equality between functions of x. This is important to realize. An IVP is a system of equations whose solution is a function. You're not looking for the value of x, for example. This is supposed to be an equality that's true for every possible value of x for which it makes sense. Like you would not take x equals -2, for example, but every other x. has to satisfy this. So you're not going to be trying to solve for x here. You're trying to compare the two expressions. They must be the same function. That's a very powerful thing. That allows you to say that how do you make these functions equal? This constant that appears in the numerator has to be the same as this 1 here. And this term in the denominator, x plus b square, has to be the same as this other denominator, x plus 2 square, for all x's. So you immediately get, like from the second one here, b equals 2. Just compare the two things. They must be equal as functions. So that's the parameter b right there. And similarly, now that you know b equals 2, just look in the first one, b minus a is 1, so a is 1. All right, so this derivative told us what the parameters are equal, at least the a and the b. One other piece of data that we have from the IVP is that g of b is 0. So 0 is the value of g of b, but the function g is x minus, let me go back. Right, sorry, it's plus x plus a divided by x plus b. This is the function. I'm going to replace the numbers. Oh, sorry, let me erase this. This would be the function at a number x. I'm going to erase the x's here and write p for them because I'm evaluating g of p. Now this is better. And we already know what a and b are. 1 and 2. So now you have an equation for p. 0 equals this expression. 0 equals p plus 1. P is minus 1. And that's it. So yes, just notice what happened in this problem. We had an IVP to begin with, even though we had a parameter inside, and we did not actually solve it just the way that we would normally. You know, first look for a function whose derivative is this, and then set the parameter, the plus c in it, set it so that the initial condition is satisfied. You know the procedure. We did not do that. Instead, we started with the given solution. We started with knowing what the IVP tells us about it. So this was quite different from the first problem that I'm going to go back to, where we actually followed the same procedure that we always do. We had the function with a parameter in it, and in order to find the max, we just found the max. We used the same procedure right here, and then just compare that max to the number 2. So those two approaches were very different, and there is no way to tell which one is going to work depending on the problem that you're working with. That's going to be up to you, as long as you understand what the things mean, every single term, like the maximum, the initial condition, all of that. If you understand what they actually mean for the objects that you have in your problem, you should be able to see a path to the solution.